Okay, good morning everyone. Welcome to this class. My name is Tian-Li from the Institute of Electronics. Just let me check a little bit. Okay. Okay, so in this class, we will the title for this class is Semiconductor Physics and Device. So in this class, we will introduce the basic and then the most important concept and knowledge that for the semiconductor. Especially, I believe that in this class, most of you who are already the graduate student or probably the future graduate student. So it could be the student that already enrolled in our NYCU, or the student that you are the future of new students in the next semester. So basically, I believe that the semiconductor physics and device in this class is pretty important for everyone's future, not only for the research, but also for your job. I think this is a very critical foundation that everyone who work in the semiconductor field. So in this class, we will basically introduce some of the key information and how we organize this class and how we do the grading and some of the procedure, how we going to run this class in this class. So this will be the introduction, and then in the second part of the introduction, we start to talk about the history of the semiconductor from the very beginning till now, and then also the future aspect. So my name is Tian-Li Wu. I'm from the Institute of Electronics and also the Department of the Electronics and Electrical Engineering. And then these classes is all welcome for the students from the different departments in NYCU. Also, as far as I know, there are some of the students from NTHU, but for sure it's also welcome because we have a big class in this classroom, so that should be able to have as many students as possible in this classroom. In my another class for the reliability, we have set the student limitation because due to the rule of the class that we're going to do the grading, there's some limitation. We cannot accommodate so many students. But I think in this class, we can try to allow everyone to follow this class if you are interested in. And this is class not only open for the graduate student, but also open for the undergraduate student, for the third year, fourth year, as long as you are interested in. So I will try my best to talk in the more easy way, so for everyone's understanding. I think for the good class lecture, it's not like we have to talk too much complicated, we have to talk too much difficult content. I think most important is to try to inspire everyone, try to talk in the more easy way that everyone can easily understand. I think that's a more part. And then my philosophy is always less is more. So as long as you can understand the basic part, that's the most important to inspiring you and encourage you to work on this field. So let's see, this is my first time in this classroom. I'm not sure that how the projector in this classroom can work. Okay, I hope this projector will work until the end of this class. Okay, so first of all, give some basic background information about the semiconductor technologies. So as you already know that the semiconductor technology becomes necessary to enable so many high performance electronics products. So in here I give you two examples that how the semiconductor technology help us for our life and also help for our some of the product we're being used for the daily life here. So as you see in the left figure, this is the Apple A17 chip. This is enabled by the world first. This is Apple A70 Pro. It's an Apple first processor built with the TSMC 3 nanometer process, and this is the first 3 nano chip. When the time that the A17 chip come out, so that's the first chip using the 3 nanometer technology, and in this A17 Pro is already made by with 19 billion transistor. So it already has a 19 billion transistor, and then it's enabled by TSMC 3 nanometer process, and also the device architecture by the 3 nanometer technology. So of course in this class we won't talk too much about the 3 nanometer or even beyond, but at least by the end of this class you will be able to understand what is a transistor and what is the general technology trend from the very old history till the planar, till the FinFET, and then probably we will just brief mention that what's the outlook for the future transistor, including some of the gate-all-around or CFET and so on, and then some of the key characteristics. Although the transistor architecture might change time to time, but the most important is that the critical electrical characteristic that we are interested in is always the same. We are always interested in the IDVG curve. We always try to, if we try to look at the transistor performance, we are always look at the drain current versus gate voltage. We are always look at the drain current versus the drain voltage, and so on, so on. So although the technology is evolved time to time, and it's in a very fast speed. After every 1 or 2 years, we have the dramatically change for the technology. But in overall, the transistor performance, what we are actually interested in, are more or less the same. This is not only limited for the advanced, but also for some specialty in terms of a compound, in terms of other technology, even with memory, with 2D, we are always look at the characteristics, something like this one. So IDVG, IDVD, and so on and so on. So by the end of this class, you should be able to familiar with these things, and then that can help you to analyze the topics that you will be work on in the futures here. And on the other hand, I also want to highlight that not only for the logic transistor based on the advanced technology, no, there's some part of the other technologies enabled by the semiconductor as well. And this is one example. I think everyone is using this adapter, that's what we call the power adapter or chargers every day. So although you might use the latest iPhone, iPad, notebook, whatever, but without the good adapter, you basically cannot be used your electronics all the day. So there's another very crucial technologies related to how we can use semiconductor to make our charger adapter more efficiency, more high performance here. So basically, if you look at the inside of this charger, this is a charger for the iPad, and the main function for this charger, which is try to convert the energy from, for example, in Taiwan, we have the AC 110 volt. So this is input voltage, and we will convert this input voltage to our targeted voltage. For example, in most of our consumer products, we only need the DC, and then we want to have the DC as lower as possible because we want to save the energy. So for example, we may need to convert the AC voltage to the DC to 1.5 volt or below. So this process is mainly to convert the one voltage, one energy to the another voltage, another energy. So therefore, the technology enables this power converting is what we call the converter. So now, if you talk to the people who are familiar with this technology, usually they won't just talk about adapter charger because this is just a typical, like the people call it in every day. But if you're more in the technical term, that's inside we have the converter technology inside this adapter. So the function of this converter is try to convert the one type of the voltage. For example, in this case, it's an AC 110 volt to our targeting voltage DC 1.5 volt. And why DC 1.5 volt? It depends on the spec of our logic chip. So inside our logic chip, sometimes we want to have 1.5 volt, we have 1 volt, even we want to lower as possible as we can. In anyhow, we have to use this converter to convert our one voltage to the another voltage. So if you look inside of this iPad charger here, this is some of the image for the PCB board inside this iPad charger, but it look more inside for the circuit schematics. You will figure out that inside this circuit, still we need to have many transistors, and the transistor, the key active transistor we are talking here is this one. This is, we call the transistor. If you have already followed the electronics or some of the basic semiconductor device in the undergraduate, so you should be familiar with the symbol of this type of the S1. This is a simplified circuit symbol for the transistor, and in most of cases we use a MOSFET, but in nowadays we try to replace MOSFET with some advanced technology, for example the gallium nitride hand, silicon carbide, and so on and so on. And not only the transistor is important, but also most of the beginner in the semiconductor field will overlook will ignore these also very important technologies that we call the diode. So the diode is also very important, crucial one in the power converter technology as you have seen here. So that's why in most of the semiconductor physics device classes, in first we will talk about some crystal structure, we talk about quantum mechanics, and later on we will start to talk about the p-n junction and p-n diode, and that's why we need to talk about the p-n junction or p-n diode, because we actually really need the diode in our certain application. And after diode, we'll start to talk about MOSFET, BJT, and JFET, and so on, so on. So most of us, when I was like a student, like you guys, as an undergraduate or graduate student, I was also very confused about why we have to learn about the p-n junction and p-n diode. But in the end, after so many years, I start to realize that it's a necessary step. You have to understand the diode, and that will help you to understand the transistor. Because in most of the advanced logic, probably we will not use the diode very often, but there's still some parasitic diodes in the MOSFET, even for FinFET. That's why we suffer so many reliability issues like ESD. In the ESD case, it's mainly due to parasitic diode, parasitic BJT. But we won't talk about ESD in this class, but just want to highlight that not only for the MOSFET, FinFET is very important, but also the diode is very important. So in general, in the domain that we discuss, this one, the power converter technology, to try to convert one energy to the another energy with this kind of the circuit topology. This is a domain that we call as a power electronics. And then inside the power electronics, the most crucial part is the power semiconductor device. So, power semiconductor device still based on the structure that we learn from semiconductor physics device is basically the MOSFET, basically the diode. For sure, we have a different design to enable to achieve our spec, to achieve our target. Okay, for sure, we will still be interested in that how the technology development from the last 10 years till the future. So this is a very nice the roadmap summary from the TSMC. So this is a slide from the TSMC, the previous chairman Mark Liu in the ISCC 2021. I think that his talk is definitely worth to be understand and worth to be shared. So you can see that from the 2010 we start to have the age until the 28, and then from the early time to 2005 to 2010, how we can make our transistor density increase is mainly based on the equilibrium scaling. So in the case of equilibrium scaling, that means that we just try to scale everything in the MOSFET in the certain equilibrium scaling. For example, we try to reduce the outside thickness. We try to reduce the channel length. We try to reduce the contact length. That's how we do the scaling. In later lecture, we will also talk a little bit about what does it mean, the scaling. But in here, just let you know that there's some the technical term that we call the equilibrium scaling. And how do we enable the equilibrium scaling? It's mainly based on the certain technology advancement. For example, the high-K metal gate, and for example, the strength silicon. So, based on this innovation, we are be able to increase our transistor density to follow the Moore's law and to have the high performance semiconductor technology. So it's by using the high-K metal gate. So as already mentioned here, introduction of the strength silicon and the high-K metal gates, that's keep our semiconductor following the Moore's law. And also beyond a certain aspect, we have figured out that it's not possible to only based on this innovation. So these two innovations not enough to allow us to keep increasing the chip performance, to keep following the Moore's law. So that's why in the somewhere between the 2015, we start to adapt the new technology, new architecture. So we need to have the innovation of the new transistor, and also including the transistor structure and also the new material. So that's including, for example, the very well known, the FinFET. And also, for example, we need to have we need to start to adapt the FinFET structure. We need to have the EUV technology. And we also need to have the high mobility channel. So these all innovations start to enable that we can continue to push the performance of our transistor to meet the Moore's law. So that's the how we already happened in the last decades here. And for sure, we need to certain idea to keeping our technology forward and beyond the right now already exist technology. And sometimes we are not only need the transistor innovation, we also need to have the design optimization based on the technology advance. So that's we call as a DTCO. So the full name for DTCO is a design technology co-optimization. So that's we call the DTCO. Because the things is that the transistor is become more and more complicated. If you talk to the design people in the last 10 years, probably they always think about what we are doing for transistor, just a simple MOSFET. If you talk to them, 20 years ago, they consider as a MOSFET. 10 years ago, they consider just a MOSFET, like you learn from the electronics, 电子学, just a circuit symbol of MOSFET, and they have no idea about what's inside MOSFET. It might be true in the past, but nowadays, our MOSFET become way too complicated. We have the planar, not only the planar MOSFET, we have the FinFET, we have the gate-all-around, we have the even for CFET, and we have so many parasitic, we have so many different design, and therefore for the design people, they have to also understand the very latest technology, and that's why they need to also learn about the semiconductor. They need to familiar with what we are doing, and in the end they can start to have the optimization based on the technology. So that's why we call the DTCO, design technology optimization. So that means nowadays for technology people, we also need to understand a bit about design. We need to understand what's their a target and how do they do the circuit. And also for design, they also need to understand what's actually the transistor architecture look like, and what's inside this transistor, and what is actually the process. So that's with all this collaboration between the design and technology people, that's why we can continue to prove the semiconductor beyond the certain advanced node, till 5 nanometer, till 3 nanometer, and beyond. And this is information coming from 2021. And then I also want to share you, this is information coming from the 2024. This is information from 2024. So you can see that after the 2020, we need to have we still need lots of innovation to try to push our semiconductor technology to meet our performance needs. So we have the several different terms here. In here, just mentioned that what technology enabled for our very latest technology. We have a 3D FinFET, we have a low resistance barrier, we have the cold cap. In here, I won't talk too much in detail. If you are interested, just you can try to look up in the internet. You will find out so many informations. And even for the N3 and N2, we start need to have a new channel material. We need to have a EUV. We need to have a metal oxide. We have need to have a self-align, and we also need to have the low damage and then low K, and so on, so on. So with all these very advanced technology stuff, we can continue to improve our semiconductor technology. So this is idea, and then this is one for the expected for the 2020, and then we expect to have more than 200 billion transistor. But with considering the heterogeneous integration with the 3D, and then some of the advanced packaging, we might achieve the target with more than 1 trillion transistor by 2013. So to achieve this very advanced technology, the fundamental part still will be the semiconductor physics and then the basic semiconductor transistor, because you have to understand the past, what actually happened in the past, and then all these although it's very old knowledge, but it's very useful knowledge that can help us to come up with some of the new ideas that can help us to address the challenges in front of us. So here is just an idea that how the real advanced transistor. This paper is already published in 2021, but still in the last year, IDEA in TSMC, they also disclosed the technology for 2 nanometer, but the papers haven't published yet, so I cannot find the information. But still, the 5 nanometer is still one of the most advanced technology so far. So it's good to understand, to read this paper, to understand that how advanced transistor can be. And in this one, this is a paper published in the IDM 2020. Although it's already been 5 years ago, but still so far, I believe it's still not that so many companies can be successfully to have a production of this technology because it's way too complicated. But also in this class, I will also want to share that in this class, time to time, we will share some of the papers like in this way, and then we will also guide you that how we usually to read the literature, because as you also you in these classrooms are the graduate student or graduate student to be, so you have to understand how to quickly read the literature and understand the key point, and then because there are so many literatures, if you try to use a Google Scholar, sometimes you will be overwhelmed by the information you will search. So you need to have the capability to do the quick screening to find out which one is most important for you. So in this paper, the title is 5 nanometer CMOS production technology platform featuring with EUV and high mobility channel FinFET with a density of the SRAM cell for mobile SoC and high performance computing application. So this is just the fifth slide from this class, but I believe the title from this paper is already the last of the term we have previously mentioned. So it's not going to be your first time to hit this term. So we have already talked about. Even you might not know the detail, but it's fine. Now you know there's a term called the EUV because we already mentioned. There's a term called the high mobility channel FinFET. That's also something we already mentioned. And also, as I already say in the first slide, the most critical characteristic for semiconductor people like us is always the IDVG. So, as you see now, this is a graph for the drain current versus gate voltage. So, once you start being involved in this class more and more, we will talk more and more about IDVG. But in this class, all of the content is already published and already being studied for more than a decade. So that means this IDVG characteristic has been already disclosed for so many years. People spend so much time. But now you see, even in the advanced technology, we still care a lot of the IDVG characteristic. So what I want to illustrate is that try to understand semiconductor probably is not that difficult as you expected. Of course, you will face some new terms in the very recent literature, but the key characteristics that we are interested in is more or less the same. It doesn't change since the last several decades. This is the idea. In the highlight of the paper, the most important figure in this paper is this IDVG curve. And in this IDVG, what we actually want to look at is, for sure, the ID means drain current. And then the VG, it means gate voltage. As being an electrical engineer like us in this classroom, what we always very interested in the current versus the voltage characteristic. IDVG just one example. For sure, in the transistor, we have so many other current versus voltage characteristic. We have a drain current, we have a gate current, we have a source current, we have a substrate current, and versus a different bias. So always keep in mind that as being the electrical engineer, electronics engineer, semiconductor engineer, we always keep the current versus voltage characteristic as our first priority interest. So in this IDVG characteristic, as shown in the TSMC paper, there's another two terms. First is an N fact, and then another one is a P fact. We will talk about N fact and P fact, but the general later. But the general idea is that with considering the N fact plus P fact, this combination is how we call the CMOS technology. So now you can start to understand why the title is showing the CMOS here, because as showing the title, we can already expect this paper is going to show the characteristic for the N fact, but also for P fact as well. So this is an implication coming from the CMOS here. So that's another very crucial terms that we will talk about later, that the detail about the CMOS and then the operation for the N fact and P fact here. But also, furthermore, you can see that the inside, because this is a TSMC paper, they only show the most critical part. They only show the part that they can highlight, they can promote their technology, they can claim that how great their technology could be. So in this graph, they only show the most critical performance and most critical characteristic. So now you see there's some text here with a debug and also with a swim. That also suggests that the performance of this transistor. The debug means the drain-induced barrier lowering that we will talk about later. Is mainly related to the short channel effect. Drain-induced barrier lowering. And then the swim here, actually the full name, swim sometimes more like the oral terms to talk about, but actually the swim is a calculation with this slope, and the real name here is a substrate hole swim. And the target is always try to make our transistor to have a swim close to 7 millivolt per decade, or even below. If below is perfect, but there's some limitation. But we try to make our transistor close to 7 millivolt per decade as possible, so we can here. So this we will all explain this later. With a very typical MOSFET with a very large dimension, larger scale MOSFET. We already talked about these issues. Okay, so then we can quickly look at for the abstract. For the one of the literature, the most important part is definitely the abstract. Sometimes we will quickly read the abstract to understand that what will be the key information here. And the abstract has once in the future you must have the chance to write for your thesis, or even you need to write for a certain publication. Then the abstract is always need to very consistent to reflect with the title and also the conclusion. So therefore, the first sentence of the abstract you can see here, this is the first sentence for the abstract. A leading-edge 5nm CMOS platform technology has been defined and optimized for the mobile and HPC application. So if you try to read this first sentence of the abstract several times, you will probably start to realize the first sentence of the abstract just the refresh of our title. So the title, what the information want to be delivered in the title is exactly the same of the first sentence of the abstract. So you can, if you try to understand, so the abstract is talking about, yeah, we fabricate 5nm platform and then we target for mobile and HPC application. So the first sentence is just talk about this one plus this one, right? So I hope with this analysis that can help you to boost your confidence once in future you need to write the English paper, because then you will understand that actually so many words and text inside the English literature in the one paper is just a refresh of the certain content. For example, the first sentence of the abstract is exactly the same like our title. And also, if you look at closely, the second sentence, this technology leading with a 5nm feature for the first time, including EUV, high mobility channel, and so on and so on. Also, this just emphasizes again what they have been mentioned in the title. Again, they mention again EUV. They mention again the FinFET, a 5nm FinFET with a high mobility channel T. So the abstract probably we can count how many lines for this abstract. So we have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But just pure refresh the title, you already wrote about 5 lines already. So that's already more than 30%, 40%, right? So just rewrite of this title. That's already come to the 5 lines of abstract. And then the total abstract is only 14 lines. We already have 5 lines here. So that's already more than 30% content. So this just want to illustrate that writing the paper is not that difficult as you see, as you expected, that it needs a very complicated grammar. You need to have very good writing skill. Actually, it's not true, because when we write the English paper, what we want to do is want to explain the things in the most simple way that lots of reader can understand. So the goal is try to very straight to the point, and then make sure that the reader can be easily understand. And we also have to again to emphasize our key point here, just like this TSMC paper. What they mentioned in the title is exactly the same in the first 5 sentences of the abstract. And if you look at the conclusion of this paper, it's exactly the same. They will mention this key feature again in the conclusion, because this is something they want to highlight. It's something they want to promote. So that's why we will always emphasize the key information again. So that's a example analysis of how we organize our English paper and English writing. Okay, so we will move on. So of course, you know that the demanding of the new applications such as 5G, AI, cloud computing, and EV, that trigger a lot of innovation for the semiconductor technology. That's why we have to keep pushing ourselves to start to generate a new advanced semiconductor technology that meet our new application. So this is also the one slide showing that this is advanced CMOS technology has been the key enabler for the innovation for 28 nanometer. Again, the CMOS term. So this is just a sixth slide for this class, the first six slide, and then you already, I think, the second time to hear about the key term for CMOS. So we will always use the same term again and again. So this is advanced CMOS technology that's based on 28 and 60 nanometer for smartphone and 4G, and also the 7 and 5. That's mainly used for AI and 5G here. And in the right hand side, this is also the EV. This is a electrical vehicle car. And inside EV, we have many technology related to our semiconductors that enable our EV car. So inside the EV, we need to have the onboard charger. We need to have the battery management. We need to have the main drive. We need to have these DC to DC, and also the high V load here. So the high V load is mainly to convert inside the EV. One of the critical technology we need to have is to convert the DC to AC, because we need to drive our wheels. So therefore we need to transform the energy from the battery. Usually the output voltage from the battery is DC, but to drive a wheel we need to have AC. So therefore we need to have a DC to AC. So that's also another example that we use for the power electronics. So we need to have a DC to DC, we need to have a DC to AC, we need to have AC to DC. So that's all needs the semiconductor to help us. Okay, so the core knowledge of the state-of-the-art semiconductor technology is for sure the semiconductor physics and semiconductor device. So which is essential for every researcher, engineer in this domain. If you like to work in this industry for your future career, for sure, it's necessary to understand the semiconductor physics and device, and not only crucial for the people working on the technology and process, but also crucial for the people working on the design, because as I say, right now we are talking about DTCO. So for the design people, if they want to optimize their system, their circuit, they also need to understand the device physics as well. So in this class, we will talk about the property of a semiconductor material, the physics of the carrier drift, the operation principle for the most important device architectures here. So in this class, we will mainly talk about the diodes, and we will talk about the MOSFETs. And also, we will talk about the BJTs. And also, we will talk about the JFETs. these are very fundamental. Of course, the nowadays transistor that you are trying to fabricate are a little bit deviated from this, but still the fundamental concept are more or less the same. So once we understand this pretty basic architecture, that's enough to help us to address the challenges that you might face in your work and in your future career. So in here, I will just quickly brief to talk about what would be the transistor we will discuss in detail in this class. So the first one, the diodes. So the diodes is a very simple structure, which is just a combination of a piece material we try to connect it two pieces of the semiconductor material, which one is a P-type, another one is a N-type. So we try to combine these two with a P-type and N-type material. And usually they are the same with the silicon, but sometimes, of course, nowadays, we try to combine the different material, but in general, the basic concepts are the same. So we try to put the two different type of doping material together. And the reason we call the N is because of this is the materials that has full of electrons, and that's more related to the N type. And the reason we call the P is because this is a material that has lots of the holes, which has a positive charge, and then electron has a negative charge. So that's what we call the N. So basically, we put the material that have a different charge, and then we try to connect it together. And to understand the diodes, the most critical part is to understand p-n junction. Because inside this junction, there's something happen. There's some physics amazingly happen and completely determine the characteristic of our p-n diode. So that's why if you have already followed the semiconductor class in undergraduate, once we finish talking about the quantum mechanics, we won't go straight to the diode, but we will for sure to first discuss the p-n junction, because what happened inside this p-n junction is completely determine the characteristic of our diodes here. So that's the first device architecture that we will talk in this class. And then the second one is a MOSFET. So the MOSFET, the full name is, first I draw the device schematic. So the MOSFET is a transistor with this structure. So first of all, we have a certain substrate in the bottom, and most often is a P-type silicon substrate. And then inside the substrate, we will do some implantation. If you start to follow the process courses, you will definitely know about the implantation. In anyhow, we will try to make this region as a N+. And then on top of this substrate, we will have the dielectric. And in most of the cases, we use the SiO2 as a dielectric. So we will have the dielectric here. Silicon dioxide. And then on top of the dielectric, we will have the gate metal. So that's a basic structure for our MOSFET. And if you look at from the top to the bottom, we have the metal here. And we have oxide here. And we have the semiconductor here. So that's why why we have to come up with the name with the MOSFET is basically coming from their structure. So the real name, the full name for MOSFET is actually the metal oxide semiconductor. So in general, in short, we call it a MOS, M-O-S here. So that's why we have this name coming from, which is mainly based on their architectures. From the top to bottom, we have a metal, we have oxide, we have semiconductor. So that's why we call the MOS here. And furthermore, this kind of the transistor is mainly operate by applying the electric field. So we call this as a field effective. Transistor. So that's why we not only have MOS term, we also have FET, because this FET is coming from this term, the field effective transistor. And then the FET term is widely used because if you look at previous this TSMC FET paper, they already use the FET here. The FET here, that's the field effective transistor. And why we call this as a field, why we consider this is the field drive transistor, because in the end, we will apply the bias here. This is a place we call the drain. And the left-hand side is a place we call the source. And in the gate metal, we will apply the VG gate bias. So this is a place we call the VD. This is a place we apply the source here. So basically, this is the full schematic for our very typical MOSFET that has a gate, source, drain, and so on. And then, in most of the case, to simplify our operation, this is a 3-terminal device. Why we call it 3-terminal? Because we have the bias in the gate, we have a bias in the drain, we have a bias in the source. That's what we call it 3-terminal. But in most of the case, we will ground the source. This is the purpose to first to simplify the operation and also to avoid some of the side effects here. So we will ground it in the source side. So now the main bias is here, drain, and gate. And you can expect once we apply the drain, for sure, we can have the current sense from the drain side. Once we apply the gate, we can have the gate current coming from the gate side. So that's why, back to our goal. Our goal is try to understand and analysis the IDVG characteristic, which is we bias at here, and then we sense, we measure the current here. So now, if you can try to understand the operation of the MOSFET with understanding of the IDVG curve, I would say you already understand 80% of our semiconductor physics and device. And then the typical characteristic for our IDVG is look like this way. So this is our typical IDVG characteristic. No matter what kind of transistor you are working on, everyone more or less showing the similar things. But the reason why the previous TSMC paper didn't show in this way is because they plot in the log Y scale. If you try to plot in log Y, this curve will become this way. This is typical with a log Y. So that's exactly the same like a previous TSMC paper. So now you see the TSMC paper is based on the 5 nanometer FinFET, which is very complicated and has so many technology innovation with EUV, with channel material, with a high-K metal gate, with so many. That's way too complicated. And then sometimes they don't disclose everything because there are so many in confidential. But if you try to look at the IDVG that's from MOSFET who have been invented in the 60 years ago, it's already show the characteristic like here. Even nowadays, we are still use this kind of a characteristic to understand the performance, to analyze our device physics. And then the third one, which is also very important, is that we call the BJT. So the BJT, the full name for the BJT is bipolar junction transistor. So if you try to just ignore the bipolar with the name here, actually the junction you already heard once, because here is a junction, right? So the junction here is the same implication like here. And transistor, everyone know about transistor. We have been mentioned transistor. So ideally, the BJT should be the one that everyone who already have the basic understanding. So the BJT is actually the transistor that just a little bit complicated than the PN junction. The BJT is a one that not only have a one p-n junction, but actually we have the two p-n junction. So we have the P here, we have N here, we have the P here. So this is structure that basically also has a junction in between. So that's why we call it junction transistor. But the reason why we call it bipolar, because this transistor involve the operation with both electron and holes. So we have the operation both combined with the electron and hole. That's why we call it bipolar. So as you know, the bi means that you have the two-way. You have the, it's just another term related to as a two, also double. That's we call it bi. So the bipolar means that there is an operation involved of the two different carrier, which are the electron and holes. Because we mentioned bipolar, that means that you have the two carrier. So you might start to wonder, and then we should have the one carrier operation transistor, which is sometimes we call it unipolar. So you know the uni is also means the one. So which transistor is a unipolar that only have a one carrier operation, which is a MOSFET. So if you try to make a comparison with a typical difference between a BJT and MOSFET is a unipolar transistor. Why this transistor is unipolar? Because under the operation, we will talk about later in detail. But generally, is once we give the gate bias, as long as our gate bias is high enough, as you know, once we apply from the very fundamental high school physics, we apply the positive gate bias, will attract the negative electron, right? This is not the quantum mechanics. We don't need the semiconductor physics. This is just a high school physics. We apply the positive on the gate bias on the one side, we will attract the negative carriers flow toward the positive gate bias. So that's the pretty fundamental basic high school physics. So that means if we apply the positive gate bias, in here we apply the positive gate bias, we will start to have the negative carrier, which are electrons, being attracted here. And this negative carrier, negative electron, which will be the only one carriers during the operation of the MOSFET. So that's why we call it unipolar. Because in the case here, we only have the electron as a main dominant carrier flow in our channel. This is the region we call the channel here. Of course, we will talk about later that in the detail, but this is, I think that's pretty straightforward, can be understood. You apply the positive gate bias here, for sure you will start to have the attracted some negative electrons in the channel. And the reason why this negative electron won't flow up is actually because we have the insulator. You still have to remember our SiO2 is a dielectric, which is insulator. Ideally, based on the Newton physics here, once you have the carrier, you have the ball throw against dielectric like the wall. There's no chance of this ball can penetrate the wall. So that's the Newton physics. So ideally, the electron cannot flow to the top because we have the insulator here. But we also apply the VD here. This is a positive VD. So we apply VD here. So the electron here cannot flow to the top, but you still have the positive bias on the right hand side, and for sure these negative electrons can only flow to the right, and then in them become our drain current. This is electron flow. So the only possibility for the electron flow is to the right and become our current. That's why you will see the current here. So what I mentioned in the last 5 minutes is just already the later we talk a detail for 2 or 3 hours for MOSFET operation. Is try to understand everything happen here. But if you can already get a little bit sense how the current flow, I think that's enough for the pretty beginner, especially we are still in the 7th slide here. Okay. And later on, we will upload this all noted PDF file. I think some of you already heard about me or probably know my lecture style. Some of you already follow my courses before. Some of you might be new, but you probably already heard about. So we will upload all these noted PDF. I also will upload the recorded video in the YouTube. So if you don't have enough time to take a note, it's fine. I think most important is to try to understand. Of course, during the break time, you can always pass by to talk to me if you miss some of the noting. Okay, so furthermore, in this class, the recent progress and challenges in develop the beyond Moore's law technology also will be reviewed. So what we have already mainly talked for the 5 nanometer, for the 3 nanometer, which is in the, if you look at this graph, this is in this domain, we have the scaling. So we try to fabricate 22 nanometer and so on. We have a 5 nanometer, we have a 3 nanometer and beyond. And in general, we call this as a more. This is a technology trend that we call as a more. But actually, in the semiconductor, we have a technology that is not necessary to follow the scaling, but there is mainly that we develop this technology to interact with the people and human environment. This is a technology that's mainly to interacting with people and environment. And this is the technology we call the more than more. So that's already included one thing that we have mentioned for the power. So power is a technology we call the more than more. And also including the RF sensor, biochips, and so on and so on. So these are the technologies that we really doesn't need to scale, but we try to fabricate the high performance of all these technology because this is enable of the certain electronics that can interact with the people and environment. Okay, so in this class, we follow this very famous educational scholar that's called Dr. Benjamin Bloom, and then he already invented the 6th level of the learning here. That's to promote the thinking in the education. So I encourage you that everyone, if you try to learn the new subject always try to push yourself to follow these 6 levels of learning. So the first level, of course, the bottom one is remember. I think everyone who follows the new subject, new courses, try to learn new things. The first thing is always remember, and second one is understand, and third one is finally we can apply, and we can analysis, and in the end, we use our knowledge to evaluate the current technology, the current situation, but also the top level is always related to the to create a certain new thing, to have an innovation. So that's the 6th level of learning. So I think for everyone here, is for the graduate student, for sure that it's going to be you will completely to realize this 6th level in your thesis, because once you have done your thesis, that's already in the level of the create, because you must create something new to address the issue that's being faced in the nowadays here. And then in this class, we try to have at least 5 levels here. We will have until the evaluate. So in this class, for sure, you don't have to remember everything, but you have to understand. You need to apply your knowledge to analyze our transistor MOSFET, and you are be able to evaluate the current technology. So this is something that we try to help that everyone in the end of this class, you are able to understand, reach to these 5 levels. So, and also these classes is based on what we call these courses is designed based on what we call the constructive alignment. So the constructive alignment is a certain of the educational teaching philosophy that try to have the very coherence for our goal with our assessment, with our teaching activity. So there are 3 pillars for these constructing alignments. The first one is we have 3 pillars here. And the first one is what we call the intended learning outcome. That's we call the ILO. So the intended learning outcome is that we hope that everyone, that's the goal of this class, by the end of this class, what you will learn. So for example, if we look at for the next slide first. So this is our ILO, intended learning outcome. By the end of this class, you should be able to, first one, explain the basic material property and device physics. So that's our goal. And secondly, apply the device physics to evaluate the operation principle of the PN diodes, MOSFET, BJT, and JFET. So that's our second goal. And third one, evaluate the current issue in the scaling technology, such as short channel effect, ultra-thin dielectric, substrate swing. That is important because once we can evaluate the current issue, and in the end, we are able to identify the problem. Once we are able to identify the problem, then we can start to propose the design to overcome this challenge, to overcome this problem in the scaling semiconductor technology. So you always have to keep in mind, when we talk about innovation, it's not that difficult as you expect that we have to try to really come up with some very amazing ideas that have the huge breakthrough. Sometimes innovation is just a matter with the problem solving. So as long as you try to solve one thing, that's already the innovation. So I believe that everyone in here, your thesis is going to solve one of the challenges in the current technology, in the current that nobody can solve. So that means your thesis is pretty also a way of the innovation. It's also very innovative, and then it's very important. So you have to always keep in mind that I know that lots of the people will criticize that when doing the research, they feel like this is not useful. They feel like it's sometimes just a paperwork. It's just a matter of try to write a bunch of the text and generate lots of figures, and then didn't realize that the value of this work. But to understand the value of your work, you first have to change your mindset. You cannot always in the mindset that pretty like the negative to think about, yeah, the thesis just fulfill the professor's expectation, to fulfill the professor's need, and then just a bunch of text figures. But if you can try to change your mindset to really trust yourself that your thesis is a problem solving, try to solve the issue. Your thesis, once you reach your problem solving, that means this is innovation, because everyone, they all agree in the industry, no matter how talent of the people, even for Nobel Prize winner, what they are doing is just actually the problem solving. They try to solve but probably what they are solving is a big problem that nobody can achieve. But it's fine, we are just ordinary people. We just try to solve a small issue. That still can be considered as innovations. So that's the first pillar. We talk about the intended learning outcome. And then the second one is we have the assessment. So basically these courses are based on these three pillars that intend to construct this class. And we have the assessment task. So the assessment, it means that we have the homework, we have the exam for sure, because that's in the end, everyone in this classroom, you need a score. And how we do the very fair evaluation, and how do we make sure that you can have the good score in the exam, then you need to practice in homework, because more than 60%, 70% of the questions in the exam are coming from homework. So for sure, we will provide the homework, and you have to do the practice to understand the key some concept of these classes. And we also have some teaching activities. So these are the three main pillars to intend to construct this class. So we already mentioned that how the goal that you will be able to achieve in this class. So try to remember this goal, because in the end of this class, on the one hand, for sure you will get one score, but sometimes the life is just not matter with the score. Sometimes life is more important to matter with what you really learn from this class. So in the end of this class, try to go through this learning outcome to check that whether you have reached this or not. That's at least for your self-checking, self-achievement. Okay, so we have the teaching, learning activity, and basically we use our courses follow for this textbook. This is from Neiman for Semiconductor Physics and Device. This is very, I would say, very useful and very basic semiconductor book. So I know there are so many different variety of the semiconductor books. Some professors, they use Professor Simon-C. Some professors, they use coming from the Professor Yuan Tao, and some they use a very complicated. But my point, as I say in the beginning, I hope that at the end of this class, everyone is getting inspiring on the semiconductor. Everyone is getting more and more interested in semiconductor. Everyone is getting more commitment, say that I will want to work in semiconductor industry. So sometimes the too complicated textbook is sometimes a little bit discouraged for everyone, at least from my previous learning activity. So I also read the Professor Simon-C book. I also read. Sometimes I would say their book is more like the dictionary. So what does it mean, dictionary? Dictionary means that when you need it, you can check it. It's very useful toolbox. It's a tool book that includes everything. They talk about everything in detail. So when you need it, you can just go look at it, and you definitely will find some very useful information. But I still pretty much like the Neiman. The Neiman, this book is sometimes being used for even for the undergraduate student. Even nowadays, for my own research, I got some problem. I still forget something. I will go back to check Neiman. So for me, it's still useful. So I highly recommend it that if you don't have the Neiman, you should have at least one. Nowadays, I believe everyone is very smart. You always find a good resource to gather the books. Yeah, you can also download from the library. I think library also provides the ebook. So anyhow, I think the Neiman is useful, although it's already very old, and some people think it's very simple. But sometimes try to explain the complicated things in simple. It's not that bad. It's very useful. So I recommend it for this book. And of course, we will upload the course slide with the lecture notes. So everything what I try to write here, I will be uploaded. And we have the videos, and we will teach everyone to use some basic band diagram software. And you can always feel free to reach me anytime if you have questions, but just try to write me an email in advance. And we have 2 teaching assistants who just left because they stay here, but basically I don't request them to sit them for the whole class, because otherwise just a waste of their time. They should focus on their research or something else. So we have 2 TA here, because the reason we have 2 TA is that we have a bunch of students. So actually, I expect we might have 70 or even sometimes beyond 70 students here. And so it's a very heavy loading for the TA to grading the homework. So the grading homework might be delayed, because you can imagine that we have 70 students here. For grading homework, it takes lots of time. So, okay. So, but anyhow, if you have any question, you can also reach the TA. They are already follow my classes, and they are all doing very well in my classes. They got very good score, and they are pretty familiar with what I'm saying in this class. And one thing I want to encourage, actually is necessary for everyone. So although in NYCU we have E3, But the problem for E3 is sometimes not very convenient, and sometimes it will crack. Just not that very convenient for everyone. So I have been running this Facebook for many years. This is my 8th year in NYCU. So we already create for this for the every semester. So try to join the Facebook. We will upload all the PDF file, all the lecture video in this Facebook. And also, if you have any questions, you are welcome to ask in this Facebook as well. And all of the urgent announcement, for example, probably due to some of the unexpected duty, I have to cancel the class or I will be delayed. I will always announce in the Facebook. So try to join this one. That's pretty important. And another thing, I think this is also make your life and my life will be more easier and comfortable on Monday morning. So I know Monday morning is very difficult time because we just had a very nice weekend. So original, we have the class on the 9 to 12. But to be honest, for me, if I have to arrive university in 9, and sometimes I face a lot of issues due to the traffic jam. So I have to drive very fast in the highway, and sometimes I get a punishment. To save my money and make my life more comfortable. Also for you guys, I know for the 9 a.m. on Monday morning is pretty challenging and then complicated. So I suggest from next time, we start from 9:30. And ideally, we have a 2 break. We have a break in between. This is a 20 minutes break, and this is 10 minutes break. But I suggest that we don't need any break. If you want to sleep, just sleep. If you want to just go to the toilet, just go to the toilet. If you want to just have breakfast, feel free. So, but for sure, we still have 1 break in between, just 10 minutes here to save the time. So we will have the class until 12:10, and then the rest will be the QA. So this is my proposal, and I have been running this style in the last 8 years. My class is always on Monday morning, so I respect that everyone, so many of you, more than 70 students in this classroom come with me on Monday morning. That shows your ambitions, your strong motivation to learn the semiconductor. But on the one hand, I also want to make sure that everyone still can fit your lifestyle with not very hurry on the Monday morning. So I think 9:30 should be agreed for everyone, at least for majority of you. If you don't agree, I cannot do anything. You have to follow. But I think 9:30 should be fine. I think in the last several experiences, nobody really against this proposal. Okay, so we have the assessment test, we have a homework, and we have in-class assignment. In the last several years class, we have 8 homework. We have 8 or 9. But the problem is that we're getting more and more students in my class. You have 8 homework times 70 students. So that means the TA has to grading around 600 homework. And then sometimes the homework is just not 1 page. The homework has 5, 6, 7 questions. So I'm considered to reduce the homework and then try to have the half. We still have 8 assignments, but half is for your self-review and half is for grading. I think that can good for TA, but also for everyone. That this is graduate class. You come here, it's not because I push you, or it's not because you require this courses. It's because of your own motivation to try to make yourself be more professional in semiconductor. So I think self-review question should be fine. We just provide you a question and provide you your answer. You can review it, and then all these question and homework at least 60% will become the question in the exam. Okay, so let's talk about the grading. So yeah, this is has to be removed. Yeah, the reason why we put the NYCU because in the past we have some students coming from the online, but we don't have online student at this moment. So we have 2 exams. So that's count for the 75%. So we have a midterm exam, which is closed book. And we have a final exam, which is open book. So the final exam is the question will cover all of the content in this semester from the chapter 1 to the last chapter. So that's why I range in the open book. Basically, you can bring anything what you want. But my suggestion is that if you bring too many things, you will confuse yourself. You will waste too much time. You can also use the internet, but in the previous experience, it doesn't help because you cannot find anything on the internet. You can find probably the sum of the equation, but if you are not familiar with, you will waste a lot of time. And then in the last year, in several years experience is always the average for the final exam, which is open book, is always lower. The average score is lower than the midterm exam, which is closed book. Because the closed book will provide you some critical important questions. So you will at least get some hint how to do it. And then as long as you are familiar with homework, you should be fine. In the final exam as well, if you are familiar with homework, you should be fine. But if you bring too many materials, sometimes it just gives you the trouble. So we will talk about the final exam once we close. Once we close to the date for the final exam. And we have a homework. That's count for 50%. And we have a tendency. That's count for the 10% here. So I don't do the attendance check very often because I believe everyone who come here is for your own motivation, for try to be more professional, to be the semiconductor people. And also, if you are very interested in this class, some of you might just watch the video later. That's also fine with me. So basically attendance is just some free score for everyone. But I still will check, but probably less than 5 times in the one semester. Okay, so that's a brief introductions. And one more thing is I want to mention that we won't have the class in the next week because I will be out for the traveling out of Taiwan, so we don't have the class in next week. And we will have the break right now, and we come back at 11. And if you have any question, just let me know. Okay.哦，好，没问题。哦，上学部的学。哦，英管系。你现在是有上研究所吗？我现在还没上研究所，因为我有1年生病。哦，对。好，没关系，我们这。我之前有修过半导体，所以有一点知识。好，没问题。那你会想要来上，对吗？为什么跑来交大，或者来上？就是老师的课在 YouTube 上，好像看过一下，老师像上台现场来讲这样。好，欢迎，没问题。我在交大这边其实也有跟其他老师做讲解。哦，对，侯老师。OK，好，没问题，好，欢迎。所以我想说来学，再多学一点，看有没有听到一些没有听过。没问题，好，欢迎，谢谢老师。好，可以。你是大几？大四。你现在上研究所吗？对，我是那个奈米所。OK， 奈米所是凯耀系，对不对？那你知道做什么？
是。
学士后，那你学士后现在是，那你本身是已经在工作，还是工作？哦，全职。那之前在哪边？哦，对，那是在哪边？哦，那你之前是什么？哦，那你这样上，你现在学士后已经是第2年级，所以你第1年级还 OK 吗？还就是follow得上吗？可以，对不对 ？OK。那你只是说提早修硕哦，所以之后你会报硕士班？哦，你是哪边的硕？电子所吗？哦，电子所硕里了。哦，那你知道教授是什么？反正总会不知道自己在教授是什么。哦 ，OK。你是之前备上的，之前推荐上的。哦 ，OK。因为那个学士后要可以跟我们一般的大学生抗体，所以你成绩应该是蛮好的。对，还好。做什么系啊？材料。哦 ，OK，好。哦，好。哦，我们基本上尽量努力啦。我们基本上过去应该是都还好，对。但是你还是，如果你都没有这个出席，你连考试都没有出席，对，真的还都考试。如果真的考不好，到时候我们再看看怎么样。哦，没关系。如果你有确定会缺席，你就先写信跟我讲。好，你现在在哪边上班？
在金源厂。
哪边？
立体。
哦，你在立体，那你做什么？
我讲好的。
哦，我们跟立体店有。
哦，真的。
对，但是 GAN 那边。
OK。
对。
所以才来做你的。
OK， 好。好。之前 TSI 课程有去。
哦，因为我是模拟组，所以我没有收到
OK， 好。
谢谢教授。
你好，我是清大大学。
好。这个是工科系，那你上研究所吗？
对。
现在在哪边？
我们两个都是庄孝新教授。
哦，庄孝新，哦 ，OK， 庄老师，我现在跟庄老师同一间4-1。
真的。
对，所以我们庄老师跟我们共用一半实验室。哦，庄老师，对，所以以后应该会这边遇到我学生，会偶尔看到我。好。对。那庄老师他们不是也要共事？对。那你们找谁共事？
多是。
对。好，庄老师很不错，我觉得跟庄老师可以学到很多东西。好，
夏教授。
你们都清大工科，2个都清大工科。对。你是清大？你是半导体硕士班？对。那为什么跨要求？
哦，因为就是类似的课，他就跟我自己修的。修这门课就是不是要毕业用的。
哦，你是清大半导体学院的。哦 ，OK。你是算硕几？
现在硕1。
那你知道教授？
里面
做什么？
是做临场排车。
哦，偏光学。
还有二维材料。
哦 ，OK， 好。
上机前可要先蛮多课，然后都可以用电。
OK， 可以。你是哪个？哦，中央是不是？你是有你现在是硕士班的吗？
就是明年要读国办。
OK， 那你教授是谁？
黄国昌教授。
OK， 好，谢谢。哦 ，OK。然后这种选项不用吗？对。那你这学期休息吗？
应该不会很，我想说可以做。
OK， 那有休2个吗？
你说这边？
对。
这休1。
哦，好，那没关系，反正就是至少你休息休1天。对，然后他们应该跟你讲就是上在TSI。
有。
对，就是这样子。那其他的我觉得其实也还好其实也不用太担心，就是我觉得这门课好好修，学到，然后 process 其实你应该上 TSI 的课程就会学到。对，所以现在可能就加强英文，我觉得加强英文，对，这样应该就还好，这样应该不用压力太大。对，好。
课纲
我们到时候会再调整。对，还不完全确定。你是那时候有什么事情吗？
对，要出国报告，所以
OK， 4月11日。OK， 你是什么时候到什么时候？
就
那种周是 OK， 好，等到我们要确定期中考的时候，会再征询大家的时间。对，看怎么样。OK， 好。你是硕士班还是？
硕士班。
你是交大电子？
才要出。看之后还要到电子所读。
OK， 那你教授找我吗？
电子所。
对。
侯老师。
OK， 好像之前有审到，对，就是这样，就是硕班嘛，然后要进 OK， 好，没问题。他那个 chip 现在回来了，可是他是寄给我还是寄给你？
好像他都一直有寄过，但我觉得他比较少。我写一下这个。
好。因为那个如果说寄给我的话，到时候手帮通知我，但手帮通知我8点才我再寄给你们。如果我明天出国，我今天回来要到2月28，对的话就是我们可以先拿到就可以先。对 ，OK， 好。
may I ask, next semester you open for the reliability
Yes.
exam, right?
Yes.
What time you plan to?
It's still Monday morning.
Monday.
Yes.
Oh,
It's a Sunday morning.
that's great. I
Okay.
plan to take it.
Okay, good, good.
And may I ask that can I take ICST courses?
I think so, but just you have to check with the ECS requirement. For me, it's fine. If you want to, which course you want to follow?
I saw. Want to take this course?
Sure.
And I'm interested about the like,
Okay, yeah, sure.
but it's open in semiconductor.
I think it's fine. For me, it's fine. I know these two professors very well. They are all teaching very good. But you have to check for the ECS program. If they say it's okay, then it should be fine. Yeah. If they can, if this course you take in ICST can be also considered credit in the ECS program, that would be great.
Yes.
Yeah.
Maybe this elective courses.
Yes. Did you make your full already? Your full?
Yeah, already.
Okay. Yes.
He suggests to apply for them.
Okay. Yeah, that's a nice course. Yes.
Yes.
Yeah.
And yeah.
Okay. And you made the AutoSATA? AutoSATA. Yeah, the one was also from Chiang internship.
Oh, Asada.
Yeah, Asada.
Yeah, I already met him.
Okay, good.
Yeah, we go to Taipei.
Okay, that's nice. Okay, good.
你是材料系清大的，你现在上研究所吗？你上交大吗？
对，
哪个？哪个？
你圣地。
OK， 好。OK， 好。
Okay, so we will continue for this class. Okay, so now I will start to review the past and also the future, which introduce some future for our semiconductor. So first of all, we have to understand that actually what is the semiconductor. I think that's this is term sometimes. For me, of course, I've been working in this field for so many years. For me, it's just a very easy to understand. But if you talk to somebody who are not have the engineering background, sometimes it's difficult to let them know what's exactly semiconductor. And also for the pretty new, the student that are pretty new to this field from the other department, probably is also sometimes confused. But the idea for semiconductor is very simple. It's just a material that has a characteristic between conductor and insulator. So I think the conductor insulator, that's the material that everyone should already learn from the high school, even the junior high school. You already know what's the difference between the insulator and conductor. So insulator, for example, the glass and plastic, these are the insulator. So the general characteristic for the insulator is that we have a low conductivity. And as I already said, we are the electronics engineer, so we are always want to use current voltage to describe the phenomenon we know. So what is the low conductivity? That means if you try to plot the IV curve, which is the current versus voltage, the low conductivity means that you try to apply the voltage, but you don't see the current. That's we call the low conductivity. That's we consider the typical characteristic for our insulator here. On the other hand, we have the material that well known is called the conductor, which for example is a metal. So consider the metal. The most important is metal has a very high conductivity. Metal has a very high conductivity. So that means if we plot the current voltage characteristic, then we just need to apply the small voltage, but we already have the very high current. And then this slope is correlated for our resistance, which is 1 over conductivity. So the 1 over resistance is our conductivity. So the conductor means that we apply a small voltage that gives us a very high current. So that's the typical characteristic for our conductor. So then back to the name of semiconductor. So if you look at the name for semiconductor, it's the conductor, but that has a semi characteristic. So as you know, the semi is kind of like the half, right? So from the name of the semiconductor is already implied our semiconductor has a characteristic like the conductor, but it just has a lower conductivity. So typically the semiconductor here, if we plot for the current versus the voltage, so semiconductor has the conductivity in between conductor and insulator, and which this resistance, the slope is here. The resistance is related to the doping inside the semiconductor here. So that gives us a great flexibility because we are able to change the different doping in the semiconductor, and that gives us a different conductivity. Sometimes we can dope very high, sometimes we can dope very low. So we can manipulate our semiconductor material either more similar to the conductor or more similar to the insulator. So that gives us a very great flexibility to control this material. So in general, a semiconductor material has an electrical conducting values that between conductor and insulator. So that's the most basic explanation for semiconductor, but that's already give us lots of the background knowledge that what actually the semiconductor can be used, because now we know this is a material that has conductivity between the conductor and insulator, and now we know that the conductivity in the semiconductor can be adjusted if we change the doping. So that gives us a very high flexibility. So if you look at for the semiconductor adaptation trend, that's from the pretty long time, from the mainframe computing till personal computing. That's one person to the one machine. Nowadays to the mobile computing, for the one person to the multiple machine, and now we have the multiple machine to multiple machine. So basically we try to leverage the semiconductor to enable this very advanced computing. And also, if you look at the things happening in the last 10 years, I think for sure that once we have the YouTube, we have the Facebook, we have the Netflix, and all these social media, and most obvious trends that we are generating the data all the day, and we have received the amounts of data all the day, so that we create a problem with the data traffic. So all of our electronics has the need to have the capability to process this data all the time. So nowadays, if you look at for your mobile phone, you are not only download, you are at the meantime you probably already watch YouTube, and then at the meantime you also try to upload your some pictures in the Instagram. So basically you are trying to receiving and generate lots of data all the day, all the time, and then you also probably have the Dropbox and Google Cloud for your some of the backup for your system. So we are facing this data traffic, so we still need a very advanced semiconductor technology enabled to handle this data traffic. And if you try to look at the history of the semiconductor, I think that with no doubt that our very respected the founder of TSMC, Dr. Morris Chang, is one of the key person in the semiconductor industry. And then recently, I think he also just published his autobiography. I think it's worth reading, because of what he tried to write is just like the very senior grandpa who just briefly talk about his life, and then his life is basically a very interesting historical story. So you just actually listen some very interesting history story, and also because this story is just exactly a line of our semiconductor. So in his autobiography, he already mentioned that he was working on the bipolar diffusion transistor, and how the scenes in the that moment that the people start to abandon the BJT and move on to the MOSFET and so on, and how do they get the big customer from NVIDIA, from Apple, and so on. I think in general it's very worth reading, so it's highly recommended. So if you look at for the 10 most important innovation in the semiconductor industry, for sure the first one is transistor. So as you know that in 1948, from the Shockley, Bardeen, from the Bell Lab, they start to invented the transistor. But the first transistor is actually not based on the silicon, it's based on germanium. But later on we found out that the silicon transistor is very good for the production because of the silicon material is easily to have, and also some of the property for silicon transistor is much stable. So the second most important innovation is silicon transistor. That's a start from the TI who tried to push for the silicon transistor as a mass production. And then the third innovation is the IC technology, which is integrated circuit. This is from the Jack Kilby from TI. And in the Dr. Morris Chan, his autobiography also mentioned that he actually was working with Jack Kilby when he was in TI. And then when he moved to Taiwan, founding TSMC, he also invited Jack Kilby to Taiwan several times. I think it's a very nice story, and also in his book, he also put some nice picture that he was with Jack Kilby. So, because usually the Jack Kilby is already the person that we only see in the textbook or in the article. It's nice to know that the Morris is actually worked with him in person in the past. So the third innovation is that we have the integrated circuit, and then the fourth one is very well known for the Moore's law. So the Moore's law was a law that proposed in the 1965, which is a law that based on the empirical observation that the transistor density will be increased, will be double after a certain time by the Gordon Moore, who is a founder of the Intel, and then just passed away just a few years ago. I also remember that the Gordon Moore, once the news related he passed away, our respective founder, Dr. Morris Chan, also made a comment that he said that the people he knows with his hint in the same age, most of people are already died. So then you can start to realize that why when he tried to write his autobiography, he was mentioned that it was the moment with writing with tears, 边写边流泪, because it's the moment that he tried to trace back all his life, and many of the people that he worked with is no longer live, and then that's pretty. It's a nice memory, but sometimes come with a sad, because that means that he is also at the most of his old friends that's no longer live anymore. So the fourth one is Moore's law. I think this is well known. We will talk about the Moore's law a little bit later. And then the fifth most important innovation is the MOS technology. So the MOS technology, including the most important, the MOSFET, and also the silicon gate, and also the CMOS. So now you can see from 1970, the CMOS has been proposed. And in our textbook, we also explain CMOS. In the nowadays, TSMC or Intel or Samsung, the latest technology, they also still work on CMOS. So that's why the understanding CMOS is very useful, because this is knowledge that you can use for all your life. And also, the sixth innovation is mainly related to the memory. So that's including the DRAM. That's including the flash memory. So I think that one of the key person to invent the flash is the C, which is Simon C. So he was a professor in the NYCU, NCTU, and the first PhD in Taiwan was actually from the previous ex-president Zhang Junyan, Junyan Zhang, and was actually guided by him. And then Professor Zhang, the previous president, was the first PhD in Taiwan who had the engineering PhD, and that was mainly guided by the Professor Simon C. So if you look at for the Professor Simon C, his autobiography, he also mentioned that he was in the Bell Lab, but he got a chance to visit to Taiwan to have a 1 year like the visiting and lecturing. And one of the reasons that he decided to come back to Taiwan is because for his family, because he wants his kids. He has a son and daughter. He wants his kids can speak Mandarin. So he really hoped that they had a chance to stay in Taiwan and learn some Mandarin. So this 1 year visiting start to inspire him, motivate him that come back to NCTU and NYCU as a full-time professor. And then he was Professor Simon C was passed away, I think, just 2 years ago, and just very recent since. So, but his contribution for the flash memory is, with no doubt, that's the great innovation, because nowadays we all use flash in all kind of electronics. By the way, this is a slide from the Dr. Moses Chen in the 2018. And why has this presentation? This is a presentation personally shared by him. And because this is 2018 is a moment with 60 years of the integrated circuit invented. So that's why he organized this forum, and then he described the 10 most important innovation. He also invited the top manager people from the Apple, NVIDIA, Qualcomm, and so on to Taiwan. And then the seventh is assembly and test. So now, starting from 1950, so some company, because the semiconductor company realized that they probably cannot do everything by themselves, because the investment for semiconductor companies is huge. You have to purchase lots of the equipment, and then you have to hire lots of people. Your fab has to run 24 hours per day, so the running operation cost is very high. So they start to realize that it needs to be certain part of the testing can be dedicated for some dedicated company. So that's why that at the moment start have the company who dedicate for the assembling and test. And then in the 1980, the Intel
start to dominate the semiconductor and also the PC market is because they start to have the microprocessor. So the microprocessor is definitely the key that enable the personal computing. So every personal computing, if you back to the 5 years ago, 10 years ago, or 15 years ago, everyone will only consider the personal computing PC that has an Intel CPU inside. And this is because of in 1970, the Intel already start to dominate the microprocessor market here. And then starting from 1970 to 1980 here, so we start to have the concept for the VLSI system design. So that's a very large integrate, that's what we call the VLSI system, very large system integrated design here. And then we start to have the fabless company coming. So from 1970 start to people in the semiconductor industry realize that probably they should be the bunch of people who only dedicate for design, and they should be the bunch of people who only work on the chip manufacturing. So that's why start from 1970 we start have the company who work on the chip design. That's what we call the fabless, because this company, they don't have the fab, they don't have the semiconductor equipment. They take care of design, and then the semiconductor company like Intel, Samsung, TSMC, GlobalFoundries, and so on, they focus on the manufacturing here. So this is a moment that Star inspired the Morris come up with the idea to have the dedicated foundry business model proposed in the 1985. So this is the historical moment in 1985, because he decided to, I think in the before 1985 already, several years before 1985, he already decided to quit the job in the TI and then come back to Taiwan. And then, to be honest, if you look at his personal growing history, he was grown in China and then moved to the Hong Kong because due to the wars inside China at that moment, and then his whole family left Hong Kong to the USA is due to the war. So he was not actually before he came to Taiwan, he has no any connection with Taiwan, but suddenly he realized that Taiwan is a good place to his startup. At the moment, still startup for the TSMC, and then he thinks this is a good place. And then I read his autobiography. I think one of the reasons is that when he was TI, he already started to see that those big semiconductor companies start to set up the branch overseas in Japan, in other places, and then in Europe. And then he want to find the place that the country that not having had any already the foreign company who set a branch. And at that moment, Taiwan for sure that nobody choose Taiwan at the moment. And then he feels that this could be the nice place. And then also another reason is that he already invited in Taiwan for the several talk, and then he is pretty motivated by our Taiwanese government who want to dedicate to the semiconductor the business. So you can see that I think this is pretty like the changing moment for the whole Taiwan, because it's back to the 2025, and then if you look at the history happened in 1985, it's 40 years ago. We all realized that why Taiwan can be
so unique in the world, and why we have this what we call the silicon shielding that protect us, and why that we are a small country, but now is the something that we can help the world is all. The main turning point is the main turning seed was happening in the 40 years ago related to this the foundry initiation in Taiwan. Yeah. So since 1985, so we start to, because due to the TSMC, we have a dedicated business, foundry business model. They decide that they only work, they won't compete with their customers, so they can work with each customer because they only dedicate for the manufacturing. So all the customer can be trust them and give them their own design, and TSMC will dedicate for their manufacturing. So since that they are getting more and more fabless company, and also that's why the TSMC can become one of the giants today. Okay, so let's look at some very historical pictures. So this is the Jack Kelpie, the TI, who demonstrates the integrated circuit. So this is the first integrated circuit demonstrated in 1958. This was a single transistor and with a component on germanium. So at the moment, in the first beginning, people consider the germanium. And also, another important is the Moore's law. As you know that even for the people who is not in the semiconductor industry, they already hear the Moore's law very often in the news. So the Moore's law is an observation that the number of the transistor in the integrated circuit double every 2 years. So the transistor will be double every 2 years. So that's the Moore's law. So if you look at this, is the bottom slide. It's from 2015. That's the 50 years of the semiconductor technology, and then can see that the Moore's law is actually very accurate to predict the performance and then the density increase for our transistor. But of course, there's always the issue that whether we can keep the Moore's law, or whether we should say the Moore's law still is dead or not. That's always the issue that already on the news in the last 5 years here. So to keep the Moore's law live and to continue to follow the Moore's law, there's several different technology and then strategy has to already invented. So you can see this slide. This is something that also very consistent with our previous introduction that discussed how the semiconductor industry try to catch up the Moore's law. So you can see the first one in the early time before 2000, we have what we call the typical Dennard scaling here. So this kind of scaling is just that we try to scale our semiconductor with one factor. So this is original device, and we have the several key parameter. The first one is this one. This is dielectric thickness. This is oxide thickness. We also have this one. This is channel length. So if you follow this conventional scaling, what we actually do is we just divide by the factor of alpha. So we have So we consider, so we put a factor of alpha. So every certain year, we just divide this factor. So that's how we call the very conventional scaling until 2000. Of course, the concept is very simple, but in the end, till the 2000, it's difficult to continue to do this scaling anymore. That's why in the end we come up with another concept that we call the equilibrium scaling. And this is enabled by the technology we already mentioned, strength silicon plus a high K metal gate. And later on, we start to have some three-dimensional transistors that we call the FinFET, and plus DTCO. So with several innovation in the end to make sure that our technology can follow the Moore's law. Of course, in the future aspect, we still have lots of innovation that can keep our transistor density increase, which follow the Moore's law as well. But of course, this is reality up to 2020. But now, if you further beyond 2020, of course, we can see the trend that the scaling is under the pressure. So this is 5 nanometer, this is 2.5 nanometer. So that means we need more innovation. But if we want to have more innovation, we need to have more talents. That's why we need you to join this semiconductor industry, because we need more talents like everyone here who are passionate, who are professional, who can commit to semiconductor and to keep our innovations happen to meet our goal. And this is so far the status. You can see that how small our transistor can be. So this is a schematic for the FinFET. So FinFET is already in this dimension, which is 10 to minus 8 meter, and our virus is 50 nanometer, and our carbon nanotube is 1.2 nanometer. So we already in the age that we do our best to shrink our technology to the extremely small dimension, even smaller than the virus. But before we come to such advanced technology, we still need to understand the evolution of a microelectronic, because that can help us to understand so many fundamentals, and this experience, this knowledge happened in the past will also come again. I think there's a very interesting some of the nice description. As you know, that for being the graduate student, I think the research, that's all we call research and development, is always a key. Not only for the graduate student, not only for your thesis, also for your future goal, future job as well. But if you try to closely look the word research, so how do we spell research? Right? So sometimes the English word, when they come out with the English word, sometimes it's very interesting. So research, in Mandarin, we call it 研究. That's right. So we try to research lots of the new things. But really try to speak the word. The research is actually the combination of read plus search. So interesting thing is that many unknown issues you will face in your thesis. You try to Google, you search, I believe more than 70% you will find out some experience or really report in the past. Probably it's not exactly, because if you look at FinFET, of course, in the past nobody has a FinFET, but gate oxide issue, etching issue, you can find the literature already reported. So always keep in mind that when we do the research, we have to leverage the past experience, the past knowledge. Of course, the Google Scholar is a very useful tool. So whatever the knowledge you wanted, you type, you always find the literature who probably already reported similar thing. Even nowadays, my research, we are working on very advanced semiconductor, but always when we face the issues, we look at the literature. We always can be finding some literature is very old. It's older than my age. It's probably, I was born in 1984, so I'm 40 years. I'm at the age of 40 years now. So some of the literature is already have the 50 years old, 60 years old, but still it's very useful. So therefore, that's why to understand, to address the new design for semiconductor, we have to understand the old history, because old history always gives us a hint. The history will come again. So the first one is a vacuum tube. That was a very, very old one. And then we have the transistor, and then the first transistor is a bipolar. And we already mentioned why we call the bipolar. It means that there's two kind of a carrier who work with each other. So which is electrons and holes. So that's why we call it bipolar, because we have the two kind of a transistor. And then later on, we have a MOSFET. So we already mentioned the structure of MOSFET, but it's good to show again, and then you will get more strong impression. And at the time, when we really talk about MOSFET, you are probably already familiar with. So the MOSFET has a structure like here. We have typically, we have the P-type substrate. We have the source, drain, and then we have the gate. And we have the gate metal. And we all know the left-hand side is source, and source will be grounded in most of the time. And we start to apply the bias in the drain side, that's we call the VD. And we will also apply the gate bias at the gate side. And since we apply the positive gate bias, we will attract the electrons in the bottom, which is a channel. But because we have the dielectric is insulator, so ideally the electron cannot flow up. But we also apply the positive drain bias on the right-hand side. So now the electron will flow to the right and become the current. And one thing that I want to illustrate that the flow direction to the right is because I use the consideration position of the electron current. But you probably already know the definition of a current, just the opposite, the direction of the electron current. So if you look at the textbook, when they say the drain current, they always show the direction inside. It's because they use the current. But for the easier understanding, it's always better to use the electron current. So the electron current flow out, that means your current flow in. I think just a matter of the definitions here. So now, again, we look at our most important one, the IDVG characteristic here. So now we all know once we start to apply the gate bias, in the beginning we don't have a current. Of course, there's some very comprehensive physics model to explain, but idea is because the gate bias is small, so your electron, your carrier here is not that your carrier density, your electron density in this region is not that high enough. So that's why when you apply the small gate bias, you won't form the current. Once at the moment your gate bias is larger enough, then your electron density is high enough, you start to form the current. So you start to see the current will increase like this way. And this is typical the characteristic at the VD, for example, 1 volt. Just remember that when we operation the transistor, we also have to apply the bias in the drain side, because then your carrier cannot flow to the drain. So you have to apply the drain bias here. And this moment start to have a current increase. It's the moment that we call the definition of these points we call the threshold voltage. VTH here. Sometimes when I was like an undergraduate student, first time to follow these semiconductor courses, it's always because we are still, our mother tongue, our native language is still the Mandarin. So we still get used to try to find the Mandarin-based textbook to understand the semiconductor physics. Or for your other courses, you probably also will try to find, for example, electronics, magnetic, whatever, engineering, mathematics. So because our native language is Mandarin Chinese, so we still get used to try to find some Mandarin books to understand. But my suggestion is that for the semiconductor physics and device, sometimes if you look at the Chinese book or Mandarin book, probably you will get more confused, because the problem is that even you see those translated name, you won't get a more clear understanding. Like the MOSFET. The MOSFET, the full name is a metal oxide semiconductor field effect transistor. But if you look at the Mandarin book, how they translate? 金属氧化物半导体场效电晶体. I think it doesn't help to us to understand more. Just still get so many confused. Also, like the term threshold voltage. Why we call it threshold voltage? Because the threshold is a term to describe that once you reach a certain moment, you start to turn on something. That's what we call the threshold. So if you look at the typical translation, regardless for the semiconductor, just a typical English, you put the threshold in the English dictionary. Threshold, the Mandarin for threshold is 门槛. So that's why we call the threshold voltage, because this is more voltage that we apply beyond this threshold, 超过这个门槛, then current increase. But if you look at the Mandarin book, how do they translate the threshold voltage? 临界电压, 门槛电压, 阀值电压, you won't get understanding. So it's getting more confused. So I would suggest that try your best. Because you just consider this is a new term, you don't have to really translate word by word, because sometimes the translation doesn't really help a lot. You will get more confused. Like a bipolar junction transistor, it's in Mandarin we call the 双载子歼灭电晶体. That doesn't help a lot. It's just getting more complicated. Okay, so that's for the threshold voltage.
which is a voltage that once we're beyond the threshold, 超过某个门槛, and then the current turn on. So this is the threshold voltage. So now, if you can understand this one, in my last 10 minutes, I try to, in the very easy way, to explain MOSFET. If you can understand, I would say you already get a catch of 80% of the concept for MOSFET. For sure, later we will talk in more detail, but I think that's enough for the very beginner to understand. By the way, just as I say that why we call this unipolar, because you can see inside the channel, the only carrier to transport become the drain current is electron, right? So that's why we call this as a unipolar transistor as well. Just to try to differentiate with a bipolar. Okay, and then later to continue to improve our semiconductor, I think the first thing is we want to have always, if you look at for our IDVG characteristic, this is a drain current versus gate voltage. Our typical IDVG is look like here. The old generational transistor has something like this one. But for the new transistor, what we want to push is always has a higher on current. You just remember that the higher current is always related to higher performance. So we want to fabricate a transistor has a higher ion. So that's why we need to come out with some innovation where mobility can be improved by the new channel mobility, new channel material, and then the purpose is to improve the ion here. So that's why we will start to adapt the germanium channel 3-5 materials here, and then this is related to the channel. This is channel, but also we will consider to use strand silicon. This is our source, this is our drain, this is our gate. So we use strand silicon. The purpose is also to improve the mobility. In here, we won't talk too much detail because every innovation here is like it requires 20 years of a dedicated study. Even nowadays, still people work on this field, try to make this better and better. But that's just an idea for your sharing here. So that's a first goal. But then we figure out that not only we need to improve ion, we also have to worry about another things. So if you imagine the one transistor look like in this way, so we have the P-type substrate. We have the N plus source and drain. We have the dielectric here, and then we have the gate metal. So, this is the place we apply the VG. But as you know, that one of our technology advance is based on the scaling. And what does mean the scaling? The scaling means that we try to make everything smaller. And one of the critical parts we want to make it smaller is this place. That's what we call the channel length. So for doing the scaling, we'll try to always shrink our channel length as smaller as possible. But we realize that once we make this region very close, there's an issue that this is a source region, as already mentioned. The source region is a region that for the N-type that has a lot of the high N-type concentration, lots of electrons, and we have a lot of electron here. And then at this moment, because the channel length is very small, we have the issue that the carrier, the electron, is being able to tunnel from left to the right. Here, even at the case Vg smaller than Vth. So now you know the Vth. Suppose we should only have the current once our gate voltage larger than threshold voltage, because threshold voltage is a criteria that once you beyond the criteria, you start to have a carrier. But the problem is that even at the Vg smaller than Vth, you don't have the carrier formation in this region. We still face the issue that the electrons being able to tunnel from left to the right because of our channel length is so small. This is related to the tunneling. And the reason behind this tunneling is because due to the quantum mechanics, quantum tunneling, we will talk about later. This is why that we have to learn the quantum mechanics. But we will explain later. In the end, the conclusion to quantum mechanics is tell us that there's one thing what we call the tunneling. Tunneling means that as long as it reaches to the very small dimension, carrier can be jumped from one plate to the other, even there's no any bias. And this gives the issue. What's the issues? Again, we look at for the ID VG characteristic, but now we will look at the log scale, because we want to see something else. In log scale, we always see the curve like in this way, and then this is what we call the VTH, so which is similar to this one. But now we have not only consider the ion, but we also consider the I off, because the I off means that this is a off leakage current when the transistor is off, when Vg is below VTF. When Vg is below VTF, suppose we want to have an I off as smaller as possible, because this I off is related to our power consumption. It's related to it's more related to our standby power consumption. That means that you turn off the transistor, if your I off leakage current is still high, you actually waste a lot of the power consumption here. So we want to make this as smaller as possible. But already explained the issue here. If the channel length is smaller, if channel length keep decreasing, then the I off can increase due to the tunneling effect. So we have another issue. in the last generation, we only have to worry about IR. But now, we not only, of course, on the one hand, we still have to keep on IR. So our goal is still keep IR increase. But we face another issue, which is our IOF increase as well. So now our evaluation characteristic, not only IR, but IOF. So we have to consider what we call the on-off ratio. So we want to make this on-off ratio as large as possible. Because if on-off ratio is large, that means our IR is large, our IOF is small. So that gives us a consideration the next generation transistor. We not only improve IR, but we have to do some innovation to reduce the IOF. So that's why in the next slide, we'll talk about how we can have the electrostatic improved by the new device geometry. The goal is to increase the on-off ratio, increase IR, but at the meantime reduce the IOF. And there's several innovation has been shown here. The first is SOI. So I think the idea for SOI is also very simple. So you can see that, as I said, the innovation is just identify the problem and solve the problem. So what's the key point for SOI? The SOI means that we actually have the insulator. This is what we call the silicon on insulator, SOI. And then from last slide, we already understand the leakage current is mainly coming from this region, right? So if we change this region as an insulator, we try to make this region as an insulator, then ideally we can eliminate this leakage current path and improve and decrease the IOF, right? So that's the idea of SOI. Because you change your substrate to the insulator, so ideally you can reduce substrate leakage current, then you can reduce the IOF. So I think the concept for SOI is not that complicated. And of course, SOI sometimes not enough. So that's why we have this tri-gate. That's what we call the FinFET. And then the last one is the advanced version of FinFET is actually what we call the nanowire. Okay, so this will be the last slide for today's class. So we will talk about a little bit more about the FinFET and so on and beyond in the next classes. So just a reminder that we will not have the class on the next Monday because I will be out. So we will see each other 2 weeks later. And then for the latest announcement and then the note PDF and then the course material, please remember to join the Facebook. You can access more the latest information. So see you guys in 2 weeks later. If you have any question, just let me know.